Hello, Tanya Laird here, and welcome to part 1 of Lecture 9 of ENGR 231 Engineering Statics. In Lecture 9, we're going to start our look at trusses, and this is a particular type of framework that we use in engineering statics to explore a lot of the basic foundational principles of structural analysis and structural design. And in this first part of the lecture, I would just like to go through basically some of the assumptions in what I will refer to as a truss member. So I'm going to title this video the truss member condition. The truss member condition. So let's see here. Now, I'm going to build this on I'm going to build the derivation here on some prior work and some prior material we have seen in previous lectures. So some things we're going to need. First of all, we're going to need to know what a pin support is, or a pin joint. A pin joint, as a review, or a pin support, is one that can transmit force in two directions, but not moment. But not moment. So if I have two members that come together in a pin joint like so, and this is just very generic here. If I try to pull on one, if I pull on these, if I pull here and I pull here, they'll be able to transmit that force between them. Or if I push up on this one here, then this one will also be pushed up as well. This joint is able to transmit force in two directions. But if I try to rotate this, if I grab this and try to rotate this joint will simply rotate freely, and the pin joint will not transmit any moment through it. But it can transmit translational forces in two directions. So and basically what we're going to look at in terms of truss members is built upon this. So I'm going to define a truss member, or I will define a truss member as the following. A truss member has pins on both ends, is perfectly straight, and has loads applied only at joints. Has loads applied only at the joints. So, in other words, I have a member like this. Oh, maybe I can show it at an angle. I have a member that, unlike my drawing here, is perfectly straight, and it has pins, or you could also refer to these sometimes as moment releases, on both ends of it. And we can have loads on these, but any loads on this are going to be applied at the joints. So I can apply loads on the joints if I like, but there's not going to be any loads applied in the middle, either either point loads or distributed loads. I can apply any loads I like at the joints, and this will stay a truss member, but it has to follow these three assumptions. Again, it has to have pins on both ends, it must be perfectly straight, and has loads applied only at the joints. And if you do this, then in that case you will have a truss member. So now, why am I describing this? Well, truss members, are kind of magic or kind of special in that if you load up if you have an object or a rigid body or a member with those type of conditions, then something special happens. And to illustrate this, I'm going to work with I'm going to look back at this member, and I think I'm going to look at this along a local axis. So if you remember from previous discussions, if something is going to be in equilibrium, it must be in equilibrium about any axis of our choice. So just like we did when we looked at the two-force body, I'm going to look at this along a local axis. So I'm going to look at a truss member where it is aligned right along the x-axis. So maybe I'll go ahead and draw an x-axis here. Actually, maybe I'll do the axis in purple and the member in black. So I have my axis here. I'll have a local x-axis and a local y-axis. And let's go ahead and draw the member. Let's just draw a nice crudely rendered truss, or truss member. Here and here, so we have 2 pins, and I'm going to call this end member A, and this end point A, and this end point B. Now let us then consider what kind of forces are applied here. Again, we recall that a pin can have forces in 2 directions, and so I'm going to apply an AY and an AX to this. And I'm going to apply a BX and a BY. And this may look familiar. This may start to look familiar if you remember our video on the 2 force bodies. And we're going to actually work through a derivation that's very similar. And let's say this whole thing has a length L. If I do a sum of moments about point A, well, I will see that AX, AY, and BX, none of them generate any moment about point A. So all that's left is B times L equals 0. And as long as L is not, or actually I should say, sorry, that should be BY here. Actually, let me do that in red for emphasis. BY here. And that should say BY times L is equal to 0. BY times L is equal to 0. And as long as I'm going to say that L is not equal to 0, because that would be kind of a trivial case, if my length is equal to 0, then I basically don't even have an object anymore. So in this case, we can say that BY must equal 0. And I can do the same thing with a balance of moments about point B. If I take a balance of moments about point B, I will get negative AY, negative moment because clockwise, times the length L equals 0. And as long as we are rejecting any trivial solution where the member length is 0, we could say that A, or AY, is equal to 0. And then if I do a sum of forces in the x direction, the local x direction here, that would inevitably lead us to that AX must be equal to negative BX. So even though I didn't initially restrict us to having only 2 forces, we can see that this basically collapses down to a 2-force body. When you restrict, when you apply, or when you have a member, when you have a straight member with pin joints, aka what I refer to as a truss member, with pin joints and no intermediate loads, or no loads applied between the ends, the member will carry only a single axial force. The member will carry only a single axial force. So if we say that the AX has to be equal to negative BX, these are equal and opposite. In other words, the forces then are essentially the same. And in terms of trusses, what this means is that truss members, I should say, because we're not quite talking about full trusses yet, just truss members will carry a single axial force, and that's either going to be a tension force or a compression force. So let's show this. Basically, they either carry a tensile force like this, and we refer to this as a positive force. We always treat, in this course and many others, in structural analysis, we treat tension as positive and compression as negative. And negative here. Oh, sorry, just a inward force, and then I'll show negative for compression here. Negative here, and so again, this is tension, and this is compression. And this comes entirely out of the fact that we have a straight member with pin joints and with no intermediate loads. And what I would like to show is why this breaks down if those are violated. So let's see what happens. Well, first of all, if the member doesn't have pin joints, then we would have a moment, then we could have a moment transmitted on the end of this. If we have a fixed end on a member, so let's go ahead and take a look at that. Let's look at, I want to break down the assumptions here and see why we have to have each of these in order for this statement to be true. So let's look at the pin joint assumption. What if a member does not have a pin joint? Like let's say it has a fixed joint on one end. In other words, a fixed joint with another member and then a pin on this end. Well, what happens in that case? Well, then I would have an AX, a BX, a BY, an AY, and an MA. And some MA. However, now if I were to do a sum of moments about A, look what happens. If I do a sum of moments about point A, the three forces AY, AX, and BX will still not generate a moment there, but I will have this MA, and I will have a BY though. BY times L again, still have that L, length L, equals 0, and now BY does not have to equal 0. Basically I just have MA equals negative BY times L. The entire truss member condition collapses. We can't, at that point we can no longer say that it will only carry a single axial force. Okay, that's fine. What about the next one? What about no intermediate loads? What if I still had pin members, but there was some sort of intermediate load? So we had pin member, and let me just say there's some load P applied at the middle. P, AX, AY, and BX and BY. Well, look what happens when I try moments now. And let's just say for convenience right now, let's say that P is applied at the middle or something like that. So let's say this is at L/2. Well, if I do a sum of moments about point A now, I will still have the BY times L, but now I will have minus PL/2. And I guess the L cancels out if this equals 0, but I then have BY equals P/2. So BY is no longer equal to 0. We no longer have that case where the member is carrying a single axial load. So that one doesn't work either. If we want to maintain the truss condition of a member carrying carrying only axial load. Sorry, not zero axial load, only axial load. Okay, next, if I want to look at, let's say I want to look at the final assumption, which is straight members. Straight member assumption. So let's say I have a really wonky member. I don't know why you would, and that is the technical term, wonky. Yeah, not a word you use very often, but this would definitely qualify as a wonky member. So let's say we have a member. It still has pins on both ends, but for some crazy reason, this is not actually my poor. Now, this time the member is crooked, not because of my poor art skills, but because of a deliberate choice. So let's say we have this really weird member that it does this kind of S-curve thing. So let's look at the forces here. And I would have an AX, an AY, and a BX, and a BY. Now, in this case, I would need not just my length dimension, but also some sort of delta dimension, like some sort of offset dimension. So I'm going to go ahead and label this L and this offset delta. And let's go ahead and do a balance of moments about joint A again. So moments about point A. The AX and AY will still not generate any moment. However, now both the BX and the BY will both generate moments. So I'm going to have negative BX. BX now will have a moment arm, this delta. So negative BX times delta plus BY times L. Plus BY times L equals 0. And now, clearly, these will not equal 0. I now have an equation that will relate bx and by, but the same kind of collapse doesn't occur, and I no longer have that nice purely axial load. Now, I should also reconnect this with our discussion of engineering models. So, if you remember previously, we've looked at many different types of engineering models, and this is another one. See, in the truss member assumption is definitely another one of our engineering models, and the reason for this is that these are assumptions. And if you really think about this, each one of these assumptions is fundamentally and completely impossible. You cannot have a joint that is purely a pin. That is an idealization, and it's a fine idealization for many systems and for all the trusses that we'll design. But it is fundamentally impossible. Even if when you have two members, if you literally had a pin connecting them together, and that's usually that's not actually what you usually have. Usually what you have is something called a gusset plate, which sometimes looks something like this. Something kind of like this, where you'd have members coming in like this, and then they're bolted in place. This kind of thing here. Bolted in place, bolted in place, bolted in place. And we treat these as pin connections and say they have 0 moment capacity because compared to the moment capacity of the members that are connecting them, they are relatively low. But they're not actually 0. And even if I actually use literal pins, like literal ball bearings or something like that, or actual machined pins, even then there would still be some friction present in that pin, and so even the most ideal pin will still be able to transmit some non-zero amount of moment. So this is not actually possible, but again, it's not 100% perfectly possible, but again, this is an idealization. Next, no intermediate loads. Now, if you're designing a truss, if you're designing a real-world truss, you can ensure that most of the loads are applied primarily at the joints, but the key word is most. It is fundamentally impossible to make it so there is never any load applied between the joints, and the main reason for that is gravity. Gravity or weight is generated all the way along a member. And so, regardless of what you do at the joints, you're going to have some load generated in the middle just from the member's own self-weight, if nothing else. But again, compared to the overall loads of the structure, the weight can be quite small, maybe 5-10% or something like that. And in that case, you can treat all of the load as coming into the joints. And straight member assumption. It is impossible to make anything perfectly straight. It is impossible to make something so perfectly straight that it is an idealized straight line with not a single atom out of place, perfectly uniform cross-section, etc. And that's the only way you could have a perfectly straight member. So again, this is an idealization, this is a model, but it's going to be perfectly fine for what we use as we go forward. So in this first section of the lecture, I just wanted to go through and discuss the truss member assumption. In part 2, we're going to discuss some of the implications of this, look at some of the theory of trusses, but I just wanted to discuss what goes into the truss member assumption, because even after we're done working with trusses, you're going to see me refer to truss members when we look at, say, frames and simple machines. So I did want to go through a brief discussion of what I mean when I say a truss member and what are the implications of the truss member assumption, or what are the types of assumptions built into the truss member condition, and what are the implications of it. So the 3 main takeaways are that a truss member has pin joints, no intermediate loads, and is a perfectly straight member. And as long as you have a member that meets those assumptions, that member will carry only a single axial load, which can be either in tension or compression. All right, that'll do it for now. Thank you all for watching. Let me know if you have any questions, and I'll see you soon for part 2 of Lecture 9 of ENGR 2301 Engineering Statics. I'll see you all then. Please let me know if you have any questions, and as always, thank you.